everyone, my name is Monica. We're happy to have you with us for getting started with the basics of IP. In this series of videos, we will be moving step by step to help you gain a systematic understanding of all aspects of the field of data communications, including data networks, switching, security, routing, reliability, BGP, and multicast. Now let's get started.
BGP has various path attributes. In this course, we will describe them in detail from the perspectives of the concept, design purpose, usage scenarios, and problems that they solve. As a distant vector feature, BGP transmits BGP routes between peers, which is similar to RIP. In addition to route prefixes, BGP also transmits a series of path attributes to peers through routes. We can configure routing policies flexibly based on these path attributes. BGP path attributes are classified into two types: well-known attributes and optional attributes. Well-known attributes include well-known mandatory attributes and well-known discretionary attributes. Optional attributes include optional transitive attributes and optional non-transitive attributes. Well-known mandatory attributes can be identified by all BGP speakers and must be contained in update messages. Such attributes include origin, AS path, and next hop. Well-known discretionary attributes can be identified by all BGP speakers but are not necessarily included in update messages. Such attributes include local preference and atomic aggregate. Optional transitive attributes are not necessarily supported by all BGP speakers. Even when a BGP speaker does not support such attributes, it accepts the routes that carry such attributes and transmit the routes to other peers. Such attributes include community and aggregator. Optional non-transitive attributes are not necessarily supported by all BGP speakers either. If a BGP speaker does not support such attributes, it ignores the routes that carry such attributes and does not advertise the routes to other peers. Such attributes include MED, originator ID, cluster list, and preferred value. This is a BGP update message, which carries BGP path attributes and some common fields. The first three path attributes, origin, AS path, and next hop, are well-known mandatory attributes and must be carried out in update messages. Next, let's talk about path attributes one by one. Let's begin with preferred value. Preferred value is a Huawei proprietary path attribute and is similar to a priority. Its value is an integer ranging from 0 to 65,535. The default value is 0. The larger the value, the higher the priority. This attribute is valid only locally and is not sent to any peers. On the network shown on this slide, BGP is deployed on three routers, R1, R2, and R3. R1 and R3 belong to AS13, and R2 belongs to AS200. In AS13, there's a route 10.11.0.0/16. Both R1 and R3 advertise the route to R2. By default, R2 cannot determine to select which route. In this case, you can configure a route policy on R2 to modify preferred value. In this example, preferred value is set to 100 for the route received from R1, and preferred value of the other route is not changed and remains as 0. In this case, the route received from R1 has a higher priority. Therefore, R2 selects this route. This modification has significance only on R2 itself and is not notified to any peers. As we mentioned in the previous course, To check the BGP routing table, run the display BGP routing table command. The BGP routing table contains all BGP routes, including those to the same destination. Among the routes to the same destination, BGP selects one route, marks it with a right-angle bracket at the beginning of the route in the BGP routing table, and adds the route to the IP routing table. Because the preferred value of the route received from R1 is increased, this route is preferred. Next, let's look at a local preference, which applies only to the local AS. This is a well-known discretionary attribute that is used to inform routers in the local AS of the optimal path for leaving the AS. The larger the value, the higher the priority. The default value is 100. On the network shown on this slide, traffic of R2 can leave the AS through R1 or R3. How does R2 determine the optimal path to leave the AS? In this case, you can configure R1 and R3 to adjust the value of local preference when they advertise routes to R2. In this example, R1 is configured to change the value to 200. Consequently, traffic of R2 leaves the AS through R1. Note that local preference is set to IBGP peers, not to eBGP peers. In the BGP routing table, we can see the new local preference 200 of the optimal route and the default local preference 100 of the other route. The local preference attribute can be transmitted only between IBGP peers. The local preference value is not lost during transmission between IBGP peers unless a route policy is configured. If a router receives a route that carries local preference from an eBGP peer, the router sends a notification message to tear down the session. Let's move on the next attribute. AS path. AS path indicates the list of all ASs through which a BGP route passes. AS path has two important functions. The first one is to ensure loop-free route transmission between eBGP peers, and the other function is to help with route selection. When the router advertises a BGP route to an eBGP peer, the router adds the local AS number to the AS path attribute. When the router advertises a BGP route to an IBGP peer, the router does not add the local AS number to the AS path attribute. On the network shown in this figure, when R1 in AS 100 advertises a route to R2 in AS 200, R1 adds the local AS number 100 to the AS path attribute. Similarly, when R2 or R3 advertises a route to another AS, R2 or R3 adds its own AS number to the AS path attribute. If R2 is connected to R4 in AS 200 and R2 advertises a route to R4, the AS path attribute does not change. AS path has four types, which are not described in detail. AS set and AS confed set are similar. AS sequence and AS confed sequence are similar. AS confed set and AS confed sequence are used in confederation scenarios. AS sequence is an ordered AS number list, whereas AS set is an unordered AS number list. This slide shows an example of AS sequence. AS set records without an order all the ASs through which a route passes from the local device to the destination. AS set helps with loop prevention and route selection. On the network shown in the figure, there are four ASs: 100, 200, 300, and 400. R1 has 2 routes, and R2 also has 2 routes. The 4 routes are advertised to R3. To optimize the network, the 4 routes are summarized on R3 to the route 172.16.0.0/16. For R3, this summary route is originated locally. Once the route is sent back to AS100 or AS200, a loop occurs. To prevent this problem, configure the summary route to inherit the AS paths of the 4 specific routes. In this example, the path information is carried in AS set. This slide shows the contents of AS paths obtained through packet capturing. By default, AS path changes only when a route leaves an AS. We can use a route policy to adjust AS path to control route selection on the next router. Now, let's look at the origin attribute. Origin is also a well-known mandatory attribute. It indicates how a route becomes a BGP route. Origin is divided into 3 types: IGP, EGP, and incomplete. IGP, which is marked as I, indicates that the route is imported through an IGP. EGP, which is marked as E, indicates that the route is learned through the EGP. Here, EGP is a routing protocol, not a set of protocols mentioned previously. Incomplete, which is marked as a question mark, indicates that the origin of the route cannot be identified. For example, if a route is imported using the import route command, its origin is incomplete. In the BGP routing table, OGN is short for origin. The next path attribute is multi-exit discriminator MED, which is an optional non-transitive attribute used to determine the optimal route when traffic enters an AS. During route selection, the route with the smallest MED value is selected as the optimal route, if all other attributes are the same. On the network shown in the figure, 4 routers belong to 3 ASs. A and B belong to AS100, and they both learn the route 1.1.1.0/24 and advertise the route to C. Because the MED value of the route received from A is smaller than that of the route received from B, C selects A as the next hop. After the MED is sent to an eBGP peer, the peer keeps the MED in the route when transmitting the route within its AS. Once the route leaves the AS, the MED is not transmitted to the next AS. By default, a router compares the MED values of only the BGP routes that are destined for the same direction and are received from the same neighboring AS. The MED is transmitted only within 2 neighboring ASs, not to a third AS. When a BGP router advertises BGP routes to eBGP peers and no policy is applied to the eBGP peers, whether the MED attribute is carried is determined based on the following conditions. If the BGP routes are originated locally, imported using the network or import route command, the MED attribute is added to the BGP routes by default if the routes are sent to the EMGP peers. If the BGP routes are learned from other BGP peers, the MED attribute is not added to the BGP routes by default if the routes are sent to the eBGP peers. When the route is transmitted between iBGP peers, the MED value is retained unless a special route policy is deployed. The MED has some default operations. On the network shown in the figure, R1 and R2 belong to AS12 and R2 connects to R3, which belongs to AS300. OSPF runs in AS12, R1 learns the route to 11.1.1.1.0/24, if R2 learns the route 11.1.1.0/24 with the cost of 100 through OSPF, and then imports the route to BGP using the network or import route command, the met value of the generated BGP route is 100. If a router imports a local direct or static route to BGP through the network or import route command, the met value of the BGP route is 0 because the cost of direct or static routes is 0. As for the force default operation, we have explained it in detail. Last but not least, we can run the default met command to modify the met value. However, this modification takes effect only on BGP summary routes and the routes imported using the import route command. Next, let's talk about the next hop attribute. It is a well-known mandatory attribute and is used to specify the next hop address to a destination network. When the router learns a BGP route, the router queries the next hop. Generally, the next hop is not directly connected to the router. In this case, route iteration is required. The default operations of next hop in eBGP and iBGP peer scenarios are different. When the router advertises a route to an eBGP peer, the next hop value of the route is set to the local source IP address. On the network shown in the figure, R1 and R2 are eBGP peers. When R1 advertises the route 11.1.1.0/24 to R2, R1 sets next hop to its source IP address. When the router receives a BGP route from an eBGP peer and sends the route to its iBGP peer, the value of next hop remains unchanged. That is, when R2 sends the route to R3, the next hop of the route is not changed. However, when the route is added to the BGP routing table of R3, the route is unavailable because the next hop 10.1.12.1 is unreachable. There are two solutions to this problem. The first solution is to use route iteration so that R3 learns the path to 10.1.12.1, for example, through an IGP. The second solution is to run a command on R2 to change the value of next hop from 10.1.12.1 to the local source IP address 2.2.2.2/32. Then the next hop address is reachable to R3, and the BGP route is available. On the network shown in the figure, the three routers are connected to the same switch and belong to the same network segment. An eBGP relationship is established between A and B and between A and C. No BGP relationship is established between B and C. When B sends a BGP route 100.100.100.0/24 to A, the next hop of the route is 10.1.123.2. According to the default operation we just mentioned, when A sends the route to C, A sets the next hop value of the route to its local source IP address. In fact, such transmission is unnecessary. Therefore, if a router receives a BGP route whose next hop resides in the same network segment as that of an eBGP peer, the next hop of the route is not changed when the route is advertised to the eBGP peer. In this way, C sends packets directly to B, bypassing A. In this scenario, A, B, and C belong to the same network segment. A and B are IBGP peers, whereas A and C are eBGP peers. When B transmits BGP route to A, the next hop remains unchanged and is still 10.1.24.4. When A sends the route to C, the next hop becomes 10.1.1.123.2, which is the interface IP address of B. The next attribute is community, which is a common attribute on large-scale networks. On the network shown in the figure, AS100 has multiple routes, including production routes and office routes. These routes belong to different network segments. The routes need to be filtered before they are transmitted to AS200. If the ACL or IP prefix list tool is used, the filtering efficiency is low. Community provides a simple method. When the routes are transmitted to AS200, the community attribute is added to the routes. For example, the community is set to 100 to 1 for all production routes, and to 100 to 2 for the office routes. In this way, devices in AS200 can distinguish all production routes from office routes based on the value of community. Community is an optional transitive attribute and a route flag, which is used to simplify the execution of routing policies. The value of community is 4 bytes long and can be decimal integer or hexadecimal notation in the format of AA to NN, in which AA is an AS number and NN is a user-defined number. The figure shows the conversion method. Generally, the value of community is not expressed in the decimal integer. There are also some special community values referred to as well-known community values, represented in a character string, and they have special purposes. Well-known community values include no advertise, no export subconfed, none, and internet. By default, all routes belong to the internet community. If a router receives a BGP route that carries the community attribute with the value of no advertise, the route is not transmitted to other BGP peers. If a routing receives a BGP route that carries the community attribute with the value of no export, the route is not transmitted to eBGP peers, excluding confederation eBGP peers. In this example, the route 1.1.1.0/24 obtained by R2 is not advertised to the ordinary eBGP peer R6, but the route is transmitted to the confederation eBGP peer R4. The concept of confederation will be described later. If a router receives a BGP route that carries the community attribute with a value of no export subconfed, the route is not transmitted to eBGP peers, including confederation eBGP peers. In this example, the route 1.1.1.0/24 obtained by R2 is not advertised to R4. Finally, let's talk about the attributes of atomic aggregate and aggregator. The two attributes are used to prevent routing loops when route summarization is configured on the network, especially on the large-scale network. On the network shown in this figure, R1 and R2 advertise 4 routes to R3. On R3, the 4 routes are summarized to the route 172.16.0.0/16. For R4, this summary route is a new one. Aggregator is used to specify the AS where the route summarization occurs. Atomic aggregate is used to inform a downstream peer that the route is a summary route. The BGP routing table of R4 shows that the route summarization occurs in AS300 and that the aggregator ID is the ID of R3. This slide shows packet capturing information. We can see the atomic aggregate and aggregator information. With this, we wrap this course up.